Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, let's get started. So it's my great pleasure today to have Christoph here, Christoph Salner. He had joined us last year for an internship, and we were working together on a particular project in the context of PACS for runtime analysis. And today Christoph is showing us a big picture that he's working on in his PhD thesis. So, go ahead.
Thank you, Nikolai. So my name is Christoph Salner, and the goal of the work I'm going to show you is to automatically find bugs, and ideally to not produce any false bug warnings while doing it. So let me explain a little bit the motivation here. So interactive theorem proving approaches are very successful in hardware development, but in software development we still have more of a mass market. So we try to have fully automatic tools that ideally just are push button for Joe average tester to use. So we enter automatic tool here, and we are doing bug finding. And bug finding is quite hard, as many people know, because you do not only need to analyze the program, you only need to analyze also need to analyze the specification, so what the program is supposed to do. And in software development, often you don't have a formal specification really, so that's especially hard if you only have like an informal specification. And here I have an example. So that's a JML notation here. So here there's some English language specification that some parameter should be positive. And that of course is like extremely hard to parse. So you might also have some Word document or some PowerPoint slides where stuff is specified. So that's extremely hard to do automatically. So we're going to try to address that problem. And let me ask you a question, like how many people have used bug finding tools? Okay, almost everybody. So what was the biggest problems in using those bug finding tools? No problems whatsoever.
Depends about with stuff that isn't necessarily relevant.
So false positives, false warnings?
False positives.
Okay. Any other problems?
Simplifying assumptions that don't carry over to real applications that I want to analyze.
Okay. That's it. Okay.
So even if some errors are not false positives, I just don't care.
You don't care?
I want to see some really important violations and not benign ones, which definitely yes, but I don't care.
Okay, so we have two people who are concerned about false bug warnings, and we're going to address that also. So the tools we're going to use for the bug finding are static and dynamic analysis, and probably most of you people know about static and dynamic analysis. So in static analysis, you do some kind of abstraction. So you abstract a little bit away usually from the execution semantics, and the goal here is to analyze all paths through a program. And since you do some abstraction, you also analyze additional paths, and then if you report a bug on one of those additional paths, then you get a false bug warning essentially. Then in dynamic analysis, it's also called testing often, you do not abstract to get the full execution semantics. And the advantage here is that you do not get those false bug warnings, but you often miss bugs because you cannot analyze all paths. And that brings me to my final motivation, which also is the motivation of a problem of two of you guys, which are false bug warnings. So people have limited time, like you. So we really want to work very hard in our tools to avoid those false bug warnings. And here I have an example from the Java world. So I'm using ESC Java. And for the case study I'm going to show you later, that's the output. That's only the warnings of ESC Java. So not about the correct. Correct, we have only the warnings. So it produced 51 bug warnings here. And I looked at all of them by hand and found that at least 14 of those are guaranteed false warnings because the behavior cannot happen under any circumstances. So it's kind of frustrating if you go through those and spend your time only to figure out that the analysis tool produce some error because your time is very valuable, so you don't want to do that.
Did you have specifications in this program?
No, no specifications.
So basically, if the user would have written invariants, DSD-Java might not have shown mnemonics.
Yes, if you would have written, and potentially you would have needed a lot of invariants to have that. And we should also say that writing those invariants is not trivial. So since we want to target the mass market, we do not really want to assume that people are really able to do those because it's not easy.
Do you think it would have been easier to put in those invariants or to discover the 14 false warnings?
So for many people, that's not really an option because many people just cannot really think on that formal level to write correct invariants. Okay, so we want to address those. And that has also been recognized and written about in research papers. For example, in the original ESC-Java paper, that's just a quote. It says, the tool ESC-Java has not reached the desired level of cost effectiveness. In particular, users complain about an annotation burden that is perceived to be heavy and about excessive warnings about non-bugs, so the false warnings, particularly on unannotated or partially annotated programs. And those are like the 99% of the Java programs you see in practice. There are like no formal specifications whatsoever. And then there also has been a more recent comparison where 5 bug finding tools have been compared, ESC-Java being one of them. And so they ran the 5 tools on programs with a total of 170,000 non-common source statements. And ESC-Java alone produced over 9,000 warnings about potential null point exceptions. So the author said that there are too many warnings to be easily useful by themselves. So against the forced bug warnings. But then it also has shown up with you, there are really 2 kinds of forced bug warnings. So the first kind I call language level forced warnings, which are cases that can never occur under any circumstances, with any parameters or any calling context or any environment. So for example, if you have like a program that says if false, and then there's some infeasible block, and the tool warns you about some behavior in that infeasible block, then I call that language level unsound warning. But then there's also the case that Nikolai mentioned, which is I call the user level unsound warning. That's a warning about a behavior that could occur with some parameter combinations or in some cases, but you still don't care about them. For example, if you have an API and you write in the specification somewhere, you should never pass a null argument into any of my methods. And then your tool creates a test case or creates some warning that passes a null, and then something bad happens, then the user might be annoyed, and the user might more be interested in other cases. So your tool should probably be able to distinguish those cases. And oftentimes here, we need really to read minds because there is no formal specification. And of course, we cannot do that either, but we're going to try to do some heuristic to do that. So to summarize the motivation, we want a completely automatic tool that should work very hard to reduce false bug warnings. And that's a very exciting problem, and many people work on that. And there, of course, there's a huge potential impact. So, and the next one is my favorite slide. So I'm just going to use a slide to ask you if you have any more questions about my motivation. Otherwise, no questions. Otherwise, I'm going to show you our approach at the problem, which is a 3-staged approach, really. And it consists of first a dynamic analysis step. So that's a dynamic analysis. Oops, I should use the other pointer.
I have a question about your motivation.
Oh.
Did you change that slide and presenting this in your
Yes. I'm going to. It's already localized, the presentation. So we started with a dynamic analysis step here. And then we have a static analysis step, which is really the core of the entire pipeline. So in that static analysis step, we're going to do the bug searching. And it's the over-approximation because we want to cover ideally all the paths through the program. And then finally, we have a dynamic analysis step where we want to remove all the language level false warnings because we're going to compile the results of the static analysis to test cases, and then we're going to run the test cases. So we can distinguish cases that we could confirm by running them from cases we could not confirm. So the cases we could confirm are guaranteed to exclude language level false bug warnings. So I have this solid no evil sign here. And then to also address the user level false warnings, we have this first dynamic step here, where we're going to run a test suite which encodes correct behavior, and we're going to try to abstract from that correct behavior to approximate the semantics, the specification. And since that's just a heuristic step, I have this more lighter no evil sign here. But before I dive into the different parts of the technical parts of the different steps, I'm going to bring up that one slide about terminology, because I ran into confusion at 2 conferences about that already. So basically it's about your convention of using sound incomplete. So what I want to say here is that a sound bug finding tool is a complete correctness proving tool. And people just often use it just intuitively relative to their background. So that's where the confusion comes from. So in logic, of course, you have a definition of sound that you have a sound tool that if your tool claims something to be true, it's really true. So if you work on a bug finding tool, then you have a sound bug finding tool if whenever your tool claims to have found a bug, there's really a bug. So you don't produce any false bug warnings. And in correctness proving, you have a sound correctness prover if whenever your tool claims to have found a correct program, there's really a correct program. So that means your tool finds all the bugs. Then conversely, so those are of course complements. So then you have a complete bug finding tool whenever there's a bug, you claim that there's a bug, you find it. So you find all bugs. And for correctness proving that you do not produce any false bug warning. So if you're thinking of sound incomplete relative to correctness proving, then just every time when I say sound, you think complete, and when I say complete, you think sound.
Why don't you then instead use the 2
blue and red phrases that you have so nicely identified here as being oblivious of which way your lattice goes?
That's even nicer way to do it. Thanks.
To try it.
Okay, so now we're going to talk about the last part of the pipeline, which we call check and crash. There was a tool check and crash. So check stands for the checking part, the static part, and crash for the dynamic part, because we're going to try to find runtime exceptions. Yeah, so in the static part, as said, we're going to use ESC Java. And ESC Java is a very powerful tool for static analysis. And like many static analysis tools, it produces the false bug warnings and both kinds of false bug warnings. So those which are language level unsound and those which are user level unsound. And how ESC Java works, I mean, we have ESC Java expert here, but I'm going to try to quickly say how ESC Java works. So it's basically an intra-procedural analysis. And you can provide pre-postconditions and invariants explicitly, for example, in the JML specification language. But it also knows the pre- and post-conditions of primitive Java operations. So whenever you do an array access, for example, it knows that the array reference should not be null, and the array index should be in bounds of the array, because otherwise you'll get some runtime exception. So and then it analyzes each method in isolation, compiles the postcondition to an assertion at the end. And then the interesting part is that every call to some other method or to some of those primitive Java operations, it's replaced by first checking the precondition and then assuming the postcondition. And then finally, the tool computes the weakest precondition of the entire method body. And that's the weakest precondition of just terminating, so of reaching the true state, because the other states are really the cases where the execution goes wrong or terminates abnormally by violating some of those preconditions. So and then ESC Java uses automated theorem prover simplified to find those cases. And we're really interested in the cases where we would get a runtime exception because of violating some of the primitive Java operations. Okay, so I said that. Okay, and so what we expect, the problems of ESC Java are the false block warnings. And here's an example. So I have this method get10, which just plainly returns 10, and then some other method which calls that and uses it as to divide by the result. And since we only do the intra-procedural analysis and do not know the specification of get10, ESC Java will assume that anything can really come out of get10, including 0. So there will be a warning about a potential division by 0 exception here. And a less expected problem of ESC Java is that also the output is quite complicated. So that's a more verbose warning. And for a pretty simple method of like 5 statements, you get a kind of explanation of the case which looks like this. And so that's basically a constraint system, a huge conjunction of conditions that have to hold in order that you reach that problematic statement. And for the average user, that's extremely hard or impossible to parse. And I guess even experts take them time to find the relevant statements, which I now highlighted here in bold. So that's also a problem of ESC Java for the mass market, really. And I'm going to try to do something about that. So how we're going to do this is basically by compiling that huge constraint system we just saw to test cases. So we're going to use our own little constraint tools to do that, and then run the test case, as I said, and then we have the advantage that we can observe the execution and then present the user the actual test case. Because most users know what test cases are and they can use it in their internal process and then check into their system, source system, and so on and so on. So the constraint solving, basically, we probably could have extended simplify to derive test cases, but we chose not to do it. Instead, we use our own solvers. So for example, for integer constraints, we use the POOC solver here. And then for floats and doubles, we currently ignore those constraints because simplify really also doesn't do much about them. And then for object references, we have our own equivalence relation-based simple solver. For arrays, similarly, also object references, and then the additional constraints for the array lengths. So we also use our insolver for that. And for the remaining non-constrained variables, we are using a random test case generator, our own random test case generator, to fill in random values. And that random generator works as follows. So it's called JCrasher. Basically, for primitive types, it has predefined hard-coded values. Like for int, it has like a 0 and a 1 here. And for object references, it has null. And then it can also crawl the testee and find rules. So basically, every method you can. So if you see a method here, b.m takes an int, produce an a, you can think of that as a rule that whenever you have a b and an int, you know how to produce an a. And then you can chain those rules together. So you chain method calls, and then up to a certain depth, and then basically you have random ways of creating values. Question?
Is there unconstrained values? Why in random?
I need some values.
Is use 0 everywhere?
If you use null or 0 everywhere, then often you violate those implicit preconditions you were worried about earlier. That oftentimes methods, are not. You're not supposed to put a null into some methods. So you want a way to randomly generate some non-null values by calling some constructors.
I guess the problem really are the constructors, or how to build recursively non-null.
Yeah, and that's how, with the crawling and the combination, that's what we're doing here. So it's a way just to generate some simple random object references here. And that works on the bytecode and does a crawling and uses Java reflection, and appeared in this JCrasher paper. So now I think I have an example. Yeah. So here we have this method swap arrays, And this was some student homework, and the specification said, so the homework was that you should swap the elements of the two arrays here, first and second arrays, first and second array, and when those two arrays have different lengths, then you shouldn't do anything. But the student ignored the last part of the not do anything and just blindly kind of swaps those elements. And of course, he iterates over the first array. And of course, if you have a second array here that is too short, then you access beyond the length of the second array, and you get a runtime exception. So that's a problem, and ESC Java points correctly to that problem. And then also produces that constraint system we just saw. So we get this. And then we feed all these constraints to a constraint server. And by the way, why there are so many constraints is because ESC Java encodes much of the semantics of Java, like the different types and lots of other stuff. So many of those are not really interesting for you to look at. So anyway, so we solve these constraints and generate a JUnit test case, which is like a standard Java test case framework. So we retrieve the solution from our constraint solver, and so in this case we create an array of length 1 and one of length 0, compile the test case, run the test case, see that it really crashes, and then we give it to the user. We show it. So that's how we exclude all the language level force bug warnings. And that appeared in that XC paper here. So, but we said that there are really two kinds, the language level false bug warnings and the use level false bug warnings. And since now we have dealt with the language level one, now we're going to look at the use level ones. Okay, and that appeared in so that's a DSD-Crasher tool. With DSD is like dynamic, static, dynamic. So we're going to add the first dynamic step to the pipeline here. And for the so we're going to do that to first exclude the user level, or try to exclude the user level force bug warnings. So like what we see earlier, there's some method here, and we're trying to get the specification from observing existing test suits. And then we're going to give that specification to ESC Java so it can exclude from its search space cases that are likely to be excluded by the user specification. But that's not the only benefit. The other benefit is also it's going to help us for interprocedural analysis. So we have, for example, in this case here, we have a caller method. And the caller method first calls for posint, and then there's some real bug here. And ESC Java will also find and point us to that real bug. But it might be that since we do not have any specification for posint, we're just going to generate random values to try to reach that statement down here. But all our generate test cases might actually crash in for posint. So if we had that specification for posint, then that would not happen because ESC Java would have generated strong constraints to point our test case generator to test cases that can actually reach down here. So that's the second motivation. And what we're going to do, we're going to use Daikon. First the main idea here. So as I said, we assume there's some existing test suite, which are all passing tests. So we're going to manually label those as correct behavior. We're going to observe that and trying to approximate here the user level specification. And as I said, that's a heuristic. So and then we're going to use the static analysis to search that space. And the advantage is that by doing that, excluded many cases which we hope contain many of the user level false positive. So then, of course, the static analysis can lead us outside of the sound space. So we're going to use the dynamic step to bring us back into the space of language level soundness. That's kind of the high level idea. And for the first step, we're going to use the Daikon. And Daikon is this dynamic invariant detection tool, which can export the invariants as JML annotations. And that's great because ESC Java understands those JML annotations. So how Daikon works is that it instruments the Java bytecode and executes the Java bytecode then. So those instrumentation sites basically just dump the values of variables that are visible at method entry and method exit. So you get a huge trace file of parameter values, return values, fields, and then there's an offline pass over that huge trace. And Daikon has a hard-coded set of template invariants, and then it's trying to instantiate those template invariants. And if some sample violates some template invariant, then it goes to throw out that invariant. Otherwise, it's so the list is shrinking kind of the invariants. And if some invariant at the end has been shown to hold for a few samples and has never been falsified, then Daikon is going to propose this is a correct invariant. And that's also where the generalization step is coming in, because those invariants are like larger than 0. And so if you have a few samples of 1, 2, 3, 4, 5, that might do the generalization that in fact the invariant is that some value is larger than 0. Okay, and then as I said, you can annotate the source code with those JML specifications. And we're going to use a simple version of Daikon that concentrates on simple invariants, where you have, for example, one integer variable is equal to some other integer variable or some other integer constant. And we're going to ignore those complex invariants because usually there are only a few samples per method. So it's not clear to us if those complex invariants will give us, if we have a high confidence in those complex invariants. And finally, Daikon expresses those invariants often relative to method calls. So we wrote a few JML specifications for those method calls so that easy Java will be able to understand that those invariants. Okay, that's the kind of the complete pipeline of DSD-Crasher here. Appeared in that ISTA paper, and if you have any questions about that, now is a good time, because now otherwise I'm going to jump to the evaluation. Okay, so we ran all of our tools on one subject to kind of give you examples of the different powers. And the subject is the Groovy system, which is like a scripting language that compiles to Java bytecode. And we used the old version, that's the version 1, beta 1, in hope to find many bugs in it. So the nice part about it, so it's open source. You get all the sources of the application, and you also get a big set of existing test cases. And those test cases have been developed completely independently of our efforts. So it's a nice case study to see if independently developed unit test cases are actually useful for our kind of tool. So and then we had to exclude some cases because Daikon quickly runs out of memory. We had 1.5 gigabyte heap space here. And that's just a few quick statistics here to show you that's roughly like a medium-sized application. So it has 170 total classes, of which we used 100. A total of 11,000 non-commented source statements, out of which we used 5,000. And we analyzed roughly like 750 methods here. And as a baseline, we used our purely dynamic test case generator JCrasher, basically just to highlight the advantages of having a static analysis. So when we limit the JCrasher search to generate 100,000 test cases and the training depth of 2, and so JCrasher picked those 100,000 test cases out of 700 million. Excuse me. But 700 million is not really a big number because so the combinations explode quickly, as you might think. And for example, for the entire Groovy set, you have already 10 to the power of 12 different combinations only with a search depth of 2. So so JCrasher takes about 3 times to compile the testee, then 20 seconds to generate those 100,000 test cases, 40 seconds to compile them, and 30 to run them. And 3 out of 5 of our JCrasher runs found like one bug or one exception, which is basically a crash in the lookahead function of the lexer. And that happens if you feed a negative integer as the lookahead distance into the lookahead function. So we observed that crash. So it's definitely language level sound because it can really happen. But most people will agree that that's probably not interesting for the user because usually you only put like a positive value into the lookahead function. So comparing this to check and crash, which uses ESC Java, that's basically what I showed you in the very beginning. It produces 51 reports, out of which at least 14 are guaranteed false warnings. And then, as I said, I looked at all of those. So 32 I confirmed to be sound at the language level. And 5 cases are unclear. So unclear means I looked at the cases for 3 minutes and couldn't figure out if it's feasible or not. And those are actually the most frustrating cases because you look at them and you can't figure out what's going on. So then you move on. In any case, so check and crash could generate test cases for 7 out of the 32. That means there's a big potential for improvement here with better constraint solving, with, for example, generating method sequence calls, sequence of method calls, generating subtypes that have some behavior, and so on. So the current versions compare as follows. So JCrasher total takes 1 minute and 40 seconds. Check and crash takes a little longer, but produces 2 orders of magnitude fewer test cases, but then finds 7 crashes as opposed to 1 or 0 crash in JCrasher. So it basically highlights the advantage of having a real static analysis as opposed to just randomly generating test cases. So what was interesting in running check and crash was that it did not find the case that JCrasher found. But it ESC Java, so the ESC Java did not even warn about the case. But instead it warned about some other issue in the same method, which occurs a little earlier in the method. Basically that there's a potential division by 0 here when you divide pos by buff.length. But when you manually look at it, then you realize that that cannot really happen because buff is a field here and it's a private field. And all the constructors set buff to a non-zero length array, and then there are no other assignments. So by looking at all the interprocedural paths, you can figure out yourself that buff.length is never 0 actually. So that's an example of ESC Java being also incomplete. Then I commented out that line, ran ESC Java again, and then ESC Java goes further and finds the other case that JCrasher warned about. Check and crash again can generate a test case and confirms the case like JCrasher did. But as we said earlier, it's still use level unsound really. And then comparing this to DSD-Crasher. So DSD-Crasher with the Daikon step at the beginning collects a 600 megabytes trace file that Daikon infers invariants, which then 3.6 megabyte compressed invariants. It takes 88 seconds to monitor, then 200 seconds to infer the invariants, and then another 2 minutes to annotate your test, the sources. And the nice thing here is that those inferred invariants were able to exclude the warning about putting a negative value into lookahead. And comparing the statistics, so DSD-Crasher takes a lot longer than the other tools. One part is that you have the additional step at the beginning, the Daikon step, and the other part is that you have now lots of invariants. So ESC Java has more to reason about, so ESC Java also takes a little longer. Then it generates a similar amount of test cases as check and crash and excludes a few cases, so we have a few fewer test cases. So that would be the evaluation and the entire pipeline. And if you don't have any questions about that.
So now you find 3 less bugs that are confirmed.
Yes.
And one you mentioned is the good one because we don't get this lookahead one. What about the other 2?
Those are problems in my analysis, so I didn't show them to you. But they could be fixed by doing a better implementation on my part.
Okay. But otherwise the message is, so this one bug wasn't found.
Yes, that's one bug we could exclude because of the bad invariance. So you clearly see that's a research prototype and not some tool you want to use for production right away.
And the 4, are they a subset of the 7, or are they 4 different ones?
I need to look that up. Yes. So if there are no other questions about the experiments, then I'm going to talk about some technical issues we had with the dynamic step at the very beginning, which are issues relating to object-oriented languages. So basically, you dynamically want to infer invariants, but then you also have static properties you need to meet. So the first problem is that Daikon really associates every execution only with a dynamic receiver of a method call. So after the dynamic dispatch, you really run one method, but that might be different than what you have in the source code, the static receiver. So I first recognized that issue when I saw that you don't get any invariants for interfaces. For interfaces, only abstract methods, no source code, never executed, so never dynamic receiver, so you never get any invariants. And that's kind of sad, because you want to have those invariants for interfaces, because the caller really made that call against that interface. So the caller probably established some preconditions, because there might have been some comments in the interface, and then the caller probably expected some outcome out of that call, because there might have also been some comments in the interface about the postcondition. So we really want to learn something about that call. But so the problem with static and dynamic receivers is not only limited to interfaces, because really it's every time you have a different static and dynamic receiver, so it might be some arbitrary redefinition of some other method. Yes, so and our current approach here is that during the tracing, whenever there's a call, we're going to look up the static receiver and then also going to associate the call with the static receiver. And right now I have a hack here for Java. So basically, whenever there's a call, I'm creating a new exception object to get the entire stack trace, method stack trace. And then in Java, if you have the debug options on, then you get the Java source line numbers of every call. So I can get the source line number of the call and then go into the bytecode with BCEL and retrieve all the calls happened at that source line number. And then I'm just going to look if any of those calls can be dynamically dispatched to the dynamic receiver. And if those differ, then I'm going to associate that method call also with the static receiver and all the redefinitions. So of course you probably see the problem here, which is that there might be multiple calls at the same Java source line. Like in this example here, we have this class C, which implements the interface I here. And then we have one source line where there are two calls that both get dispatched to c.m, but one is against the static receiver I, and the other one is against the static receiver C. So without knowing the value of cond, we cannot really decide from which call side we made that call, unless we have more execution information during the tracing, and PEX would be one way to get that information. So I'm looking at Nikolai, but there's might also be a simpler solution where we could rewrite all the call sides, because at the call side we know the static receiver already. So we could encode that information into the method signatures by rewriting all the method signatures, and then we wouldn't need the expensive analysis of PEX here, or PEX-like, because we are working on Java and you're working on .NET. So that's the first problem. The second problem is a little bit more general. It has to do with behavioral subtyping. And behavioral subtyping is a good object-oriented development practice. It's or is called subcontracting in Eiffel, and I think also Spec Sharp has behavior subtyping features, but you guys know lots more about that. So basically, behavior subtyping says that the contract of a redefinition of a method should obey the contract of the redefined method. So it's only allowed to weaken preconditions and sanction postconditions and not do anything else. So the advantage here is that a caller can rely on the contract of the static receiver, because no matter to which other method the call gets dispatched, it is guaranteed that the callee obeys the contract of the static receiver. And JML really enforces that rule. And it does this by, so here's an example how in JML, in Java, how that might look like. So you have some superclass here, and then a method M, and then here a precondition requires, and then some condition P, and then a postcondition Q here. And then you have a redefinition of that method in C. And in the redefinition, you have to use the keyword also in JML. Excuse me, just to remind you that the definitions, the pre and post conditions you give here are really only in addition to the pre and post conditions you have given in the superclass here. So and then JML has those rewrite rules internally that it computes the real pre and post conditions of C.M by ORing together the preconditions of the superclass and the subclass, and then by building this conjunction of precondition of the supertype implies a postcondition of the supertype, and the precondition of the subtype implies a postcondition of the subtype. So that's nice because then we have enforced that the precondition of the subtype is really weaker than the precondition of the supertype, and the opposite for the subtype. But now what you're going to do in the dynamic invariant detection. So what Daikon is doing, let's assume, we make an example here. Let's assume that all our static receivers are equal to the dynamic receivers, so we don't run into the problem we had before. And then we have we observe a couple of executions, and for super.m, so super.m in all our cases returned 1, and C.m all the time returned 0. And then what Daikon is doing is just to annotate super with postcondition 1 and C with postcondition 0. And for C, without really caring about that, there might be some specification for super already. So that creates a problem because with the rewrite rules we just seen, we get a postcondition for C, which essentially said that the result has to be 1 and 0 at the same time. Because so implicitly we have a precondition of true here, if you don't say anything. So that's basically the rewrite rule we saw last time, which simplifies to this, which is a contradiction. So essentially that's false. And so that's completely unsatisfiable because by default a method cannot loop forever or throw any exceptions if you don't specify it. So there cannot really be any implementation that satisfies this specification. And that's clearly a contradiction because we just observed cases that run through the method and produce something. So that's what we want to avoid. And really the problem here is that the preconditions of C and super overlap. So those calls to C.m could have also been made to super.m. And if the code would have done that, then our previous solution would have solved the problem because it would have associated the calls also to the super class. But code doesn't always do that. So we need to find the correct, I mean the highest possible static receiver of a call ourselves. And yes, so we have two potential solutions here to find the highest possible or correct static receiver. So the first one is very fast because it just over-approximates the highest possible static receiver by associating the call with all potential with all redefined methods. Basically, so it weakens the postcondition of those supertypes, which of course imprecise because it might have go too high in the inheritance hierarchy. And then the second case is the second solution is more precise, but also slower, naturally. So just to give you like the idea how that the goal or how it would principally work is, so we have the PQRS from the pre and post conditions of like before, and then what we want to do is weaken the post condition of the supertype to also include the cases we've seen for the subtype. So we push the S of the subtype, sorry that I'm in your way, also to the up to the supertype. And for the fast approach, we're going to do that for all supertypes. And so in our example here, it would be, so the preconditions are both true for both classes. So we would push up the 0 here, the postcondition, also to the supertype. So we get 1 or 0, and you see that with the rewriting rules, we still get the more precise postcondition in the subtype. Okay, and so one way to implement that would be to explicitly rewrite all those postconditions after the fact. And there might also be other rewriting schemes to get a little bit more precise here. But we think we have like a faster approach, which is basically an extension of what I showed you before. So instead of just going up to the static receiver, we could go like beyond the static receiver in the inheritance hierarchy. And in the fast and imprecise solution, basically just associate the method call sample with all of the super definitions. And the advantage here is you don't need to do that explicit rewriting of the postconditions, which so if you do that, you might also want to do some constraint solving calls to simplify the the result of those rewritings. That might be tricky and expensive. So we can avoid that. Yes, so that's already said. So you get the imprecision because you might have over-approximated that receiver, and that's why we also have the the more correct approach. So here also you don't do the explicit rewriting, but we're going to organize the entire invariant detection a little different. So we're going to do 2 passes of the traces. So in the first pass, we're only going to infer the preconditions. And then in the second pass, only going to associate a sample to those supertypes where the sample satisfies also the precondition. And so the goal is to find the correct static receiver. And since you do the 2 passes over the entire trace, it's more expensive, but you get the precision. And that idea was in that XC poster here in 2006. Oh, and my advertisement slide to show you like where the tools have been used. So JCrasher has been used in teaching and in Berlin and in research, North Carolina State, and JCrasher at more places. And so that would be my tools. And for this week, as Nikolai already said, we are working on a more precise version of Daikon, which tries to be more precise by using pecks and collecting path conditions and using those path conditions to have more precise pre and post conditions, because we get all the conditions from the execution and do not need to rely on the predefined hard-coded list of templates that Daikon has. And for future work, it would be nice to apply those static dynamic hybrids to other areas like, security, the obvious stuff like compilers, model checking, and other areas. And an entire different thing we have done recently is to test database schemes. So basically, a database specification is also a list of constraints. And then so we have found like a subset of constraints which we can solve very fast. And then that will appear in an ASE 2007 paper. And it can also, if you have a solution, you can also generate test cases, so database instances. And it would also be interesting to apply that to UML. And finally, so you see George Tech there as an affiliation, but right now I'm at some other university. And the question, so I want to ask you where that might be, and I give you one hint. So in the last week's student newspaper, we had this ad. It says, "Welcome law students, reduce your impact." So which university would that be? Any ideas? Nikolai. So it's Eugene, Oregon. And here, of course, it means reduce your impact on the environment. Anyways, thank you. If you have any questions, I have my tool pipeline here. Question?
I was wondering, many of the technical problems you see seem to come from the fact that DSD-Crasher is modular. So the behavioral subtyping problems, the problems that you cannot look at all possible overrides, you cannot look at all possible call sides of a method. On the other hand, in your context, we have the whole program, you can execute it. So wouldn't it be a smarter choice to take a program verifier that is a whole program verifier instead of a modular verifier? I mean, if such a tool existed in a reasonable quality.
So there are two answers, I think. So the first one is, so the behavioral subtyping stuff at the very end was really a problem of Daikon, the first step, the dynamic analysis step. Then EC-Java is indeed a modular analysis, but then, so the nice thing is it scales really well because it is modular. So we try to preserve the modularity, the scaling up to huge applications. But there might be interesting tools that do whole program analysis. But in that work, we did not look into those. Because EC-Java was available for Java. Very nice tool, so we went with that.
I have one more question. It looks like you have solved all these little problems. So why isn't everyone using it yet? What's the remaining biggest obstacle?
So there are a few low-level technical issues, like EC-Java has been adapted to like JML and has been adapted to Java 1.4, but not really beyond that. So the focus is not really to have in EC-Java, I think, to keep up with Java and all the low-level technical advances, but more to use it as a research platform for other stuff. So it's not really, doesn't really support all the cases that industry probably would want to have.
Otherwise, for Java 1.4, it basically does everything we are all dreaming about. Or what would you characterize as the biggest problems?
So I thought about using that in an industrial application, basically during my Google internship. But since they really want to keep up with the latest versions of Java and all the latest features, there was probably not enough interest for that. So there are like two directions, right? One, you want to have the interesting ideas, and one, you want to also cover all the features. Like European PACs to the same issue, I guess. Other questions? No questions. Okay.
So Christoph will be staying here for the entire week. If you want to talk with him, he's sitting in my office just nearby. And so I'll speak again.